Hello everyone. This year at IMS, Skyworks is very pleased to be introducing a new industry-leading LNA called the Sky 67151. This device as you can see from the data here, this device is delivering best-in-class noise figure over a very wide range of frequencies from about 500 or 600 megahertz up to around 4 gigahertz. The evaluation board noise figures you can see on this plot right here, they're roughly 0.25 dB at 900 megahertz and 0.35 dB at about 1850 megahertz, up to about 0.5 dB at 2500 megahertz, and roughly 0.7 dB at 3600 megahertz. The device can be biased over a wide range of supply rails and biased current, and that's one of its key attributes. The data you see here is a snapshot of the performance at a single frequency of 1850 megahertz. And what actually of the full frequency range from 850 up to 3800 megahertz. And you can see plots of noise figure versus IDDQ for the device here. And the purpose of showing this is to show you that for currents above 40 milliamps or so, the noise figure performance at any frequency is very flat. As you take the bias current down to say 20 milliamps or so, you'll notice the noise figure performance starts to degrade ever so slightly, but it's still very, very good noise figure even at 20 milliamps. So the point of that is, depending on the efficiency requirements of your application, you can bias successfully with IDDQ values anywhere from say 20 milliamps up to about 80 or 90 milliamps. This particular slide not only shows the very good noise figure performance of the LNA, but it also shows the gain and noise figure performance of the device over temperature. And if you notice on the x-axis, the temperature goes from minus 40 degrees C up to plus 105 degrees C. And if you can take a look at the gain plot, which is in green up there, at minus 40 C, the gain is about 21 dB. And even up to plus 105 C, the gain is still in excess of 20 dB. So there's less than 1 dB of gain roll-off over that full minus 40 to plus 105 C temperature. Another thing is you can see this device had a noise figure of roughly 0.3 dB at 25 degrees C. When we took that cold to minus 40, we essentially went into the measurement limitations of our equipment, right? Because we're dropping down to about 0.1 dB, and I don't believe anybody from Agilent can sign up to any accuracy down at noise figures that low. But the point is, it was at 0.3 at 25 degrees C, and it dropped that low. Now, as the temperature goes up to 105 C, you can see that the noise figure has only climbed to about 0.53. And this is not noise figure of the device, but it's a noise figure of the entire evaluation board. So this is SMA to SMA with the matching components and everything. What you see here is a plot of 4 traces with 4 different evaluation boards that are tuned for the 800 band, the 2 gigahertz band, the 2.5 gigahertz band, and the 3.5 gigahertz band. And it shows you the effect of increasing IDDQ on IP3. So what it basically tells you is if you want to run the device with a IDDQ of 30 milliamps, you're going to see an output IP3 in the 30 dBm range. But as you increase the IDDQ, you come up to a higher and higher IP3. Now that kind of peak in the middle there, that's going to be very match dependent. So some matches that you have on the output of the device will respond progressively with higher IP3 as you go to higher and higher current. It's just that particular match had a notch response in IP3 at about 60 milliamps or so. But that would be match dependent, so that's something you could play with. This is just a matrix of some of the more detailed RF performance for the various bands. You can see the input return losses are in the minus 11 to minus 12 dB range. Output return losses, we typically achieve close to a conjugate match with that side of the amplifier. So you'll see S22 values of minus 18, minus 20, minus 22. The gain slope numbers and the ID to Q slope numbers are very, very small, and you've already seen that on the other graph where there was less than 1 dB of gain roll off over the entire temperature range. I bring this set of data up because it's actually talking about a different part called the Sky 67023. This is essentially the same part, but it's done in an older half-micron p-hemp process. So you can see at this frequency of 2.6 gigahertz, the evaluation board noise figure was roughly 0.9. The 67151 noise figure is roughly 0.5, so a very big improvement in noise figure from going from half micron to quarter micron. Also, the gain of the quarter micron device is about 2 dB higher at that frequency, so you have more gain, which you need from a cascaded noise figure standpoint anyway, and a much, much lower noise figure. And just a little side point here, if you were to look at the data sheet on the web for this part, the 67023, all you would see would be this data essentially at this one frequency. But much as we've done for the 67151, where we've tuned it from 500 megahertz up to 4 gigahertz, that can also be done for this part as well. It's just that at any given frequency, the gain will be slightly lower and the noise figure will be higher. But the flexibility to tune it is far beyond what is shown in the data sheet, and that's something to keep in mind, especially with single-stage devices. There's really very rarely anything internal that keeps you from changing the frequency of operation, right? So don't feel handcuffed by what the data sheet says as max and min frequencies. With multi-stage amplifiers, that can become more of an issue, especially if you don't have access to the interstage match. But for a device like this, it can easily be tuned over a very, very wide range of frequencies. And if you don't need the super low noise figure, a device like this will be a little bit cheaper than the other one as well. So it really just depends on the requirements of your application and your marketing department. Okay? So in terms of design support from Skyworks, we offer standard evaluation boards that all use the same layout and schematic with only slight changes in the LC matching components to the boards, right? It's very easy to get 20 to 30% bandwidth with a specific tune, and therefore we offer standard tunes from, say, 700 to 1,000 megahertz, 1,600 to 2,200 megahertz, 2,300 to 2,700 megahertz, and then 3,300 to 3,800 megahertz. Okay? On the website, we offer the embedded S parameters with the noise parameters in the file, so you can easily get into your ADS simulator and experiment with different input matching topologies and trying to trade off return loss versus noise figure, that kind of thing. And Skyworks applications engineering on a routine basis does custom tunes of this part for very specific applications. An example is we've done some very broadband applications from, say, 800 megahertz to 2100 megahertz for cable TV set-top boxes, all with good return loss, very good noise figure, very good linearity, and it's turned out to be an extremely flexible part that just happens to have the best noise figure going right now, and that's a pretty cool thing. To close this short presentation, I just wanted to give you more of a brief overview of an exciting new product family that we have, and it consists of some very high power PIN diode based transmit-receive switches that have insertion loss values that are somewhat lower than a PHEMT switch, and also power handling capability that goes well beyond what any type of PHEMT switch could handle. You can see circled in red, that's the typical spot on a transceiver lineup for the switch that we're talking about. And here you see a pretty complete matrix of what we have right now in terms of these transmit-receive switches. And you can see power levels going anywhere from about 75 watts up to 100 watts, and now we're just about to release a 150 watt single pole double throw switch. Okay. But very, very high linearity, very high power handling capability, and very low insertion loss compared to some of the other technologies out there. It's kind of interesting because diode expertise in the industry is something that's been around for a long time, and it's kind of dwindling away, but there's still a great demand for really high performance high performance, low loss, high power switches. And that's where these PIN diodes fit perfectly. Here's an example of our 100 watt switch, the Sky 2210, and it just gives you some of the performance. IP3 of about plus 55 dBm. Insertion loss is very low, and about 0.4 dB, and about 44 dB of isolation from the two paths inside the switch. Again, here's some data plots showing the insertion loss of the device over frequency, and some of the return losses as well. Finally, this is just a little bit of a marketing blurb about some of the applications for this type of switching capability. But this is a very active product line for us now, so there are many products now that are in the pipeline to bring out to kind of flesh out this portfolio of switches. That is it, and I thank you very much.
Thanks, Al.